lab, we focus on a pulley system and acceleration based on the Newton's second law, F equals ma. In a pulley system, acceleration depends on the difference between two masses. When mass 1 is greater than mass 2, the system tends to accelerate in the direction of the heavier mass. Theoretical acceleration can be calculated by using gravity. In real life, pulley systems are used in elevators, construction cranes, lifting systems, and many other things. And in this experiment will help us to understand how forces and mass affect motion and how the real-world factors like a friction impact results. The materials used for this lab was a pulley system, a single and a double pulley, a string, a mass holder and masses, a motion sensor, a computer with graphing software, which was Capstan, and last but not least, a stand and a clamp. The procedure for this lab was to set up a single pulley system in which mass 1 will be greater than mass 2. Then we will place mass 1 in a higher position and begin the recording. Once we release the masses and allow the system to move, we will catch the masses before they hit the floor or the pulley, and we will repeat the process to collect accurate data. Then we will select the new masses between 50 grams and 200 grams with a difference greater than 50 grams. Then we will add the extra pulley mass to mass 1, and then we will set up the double pulley system and repeat the experiment. We will run the multiple trials until the straight line graph is obtained, and last but not least, our test different masses combinations to find the acceleration closest to 0. The formulas used for this experiment were the following. We started by using the theoretical acceleration with one pulley of equivalence, which consists of acceleration equals m1 minus m2, which is mass 1 minus mass 2, over mass 1 plus mass 2 times our gravity. Then we proceeded to use another theoretical acceleration, but now it has to be calculated through the two masses of the two pulleys, which would be acceleration 2 equals negative parenthesis 2 times mass 2 minus mass 1 parenthesis over 1/2 mass 1 plus 2 times of mass 2, again multiplied by gravity. Then our percent error formula consists of percent error equals theoretical acceleration minus experimental acceleration over our theoretical acceleration again times 100. In this experiment, we began by calculating the theoretical acceleration with one pulley by using the following formula again, which is acceleration equals mass 1 minus mass 2 over mass 1 plus mass 2 times our gravity. So for our masses, mass 1 was set to be 50 grams minus the 10 grams of mass 2, then over 50 grams plus 10 grams times our gravity, which is equivalent of 9.8, will give us a result of 5.53 meters per second squared. Then we're gonna go ahead and annotate it in our chart as well with our masses so that we don't lose track of them. Then for our second table is through the actual experimental acceleration, and we have to calculate percent error, and that's through the formula of percent error equals theoretical minus experimental accelerations over our theoretical acceleration once again times 100. So our experimental data was determined from the graph that we obtained, and that will be our m value, which was said to be 5.97. So once we plug that into our formula, it should look like 6.53 minus 5.97 over 6.53 times 100, which will give us a result of 8.57% error. And we're just gonna go ahead and annotate our experimental acceleration. For our table 3, we have to calculate our theoretical acceleration once again, but by using our new masses, which mass 1 was said to be 100, mass 2 was said to be 20, and we use a formula of acceleration 2 equals negative 2 mass times mass 2 minus mass 1 over our 1/2 of mass 1 plus 2 times mass 2 times 9.8, which is our gravity. Then we plug in our values, which will look like negative parenthesis 2 times 20 minus 100 over 1/2 of 100 plus 2 times 20 again. Then we multiply all of that times 9.8, which then if we run it through the calculator, it should give us a value of 8.4 meters per second square. So we're gonna go ahead and annotate it once again. Then for our last table, we have to calculate it again, our percent error, but by using our new experimental value, which then we plug into the formula of percent error equals theoretical acceleration minus experimental acceleration over our theoretical acceleration times 100, which then will look like something like 8.4 minus 7.8 over 8.4 times 100, which then it will give us a value of 7.02% error. And this is achieved by putting in the calculator, and our value was derived from, once again, from the m value of our graph. Some of the challenges that we faced during this lab was the friction in the pulley, which caused a slowdown in the motion and affected the acceleration values. Then there was an imbalance or misalignment in the pulley, which will cause an uneven movement and inconsistent data. Then we have some string issues, which causes lack of stretching, which changed the forces that was transferred. Then we have some mass measurement errors, which by forgetting to include the pulley mass or misreading of the values. And last but not least, the motion sensor difficulties, which cause an inconsistent readings or trouble capturing smooth data. In conclusion, this experiment showed us that acceleration increases when the mass differences increases. Also, that when masses are nearly equal, acceleration is closer to 0. As the experimental values were close to the theoretical values but had some percent errors, then the double pulley system had more error than the single pulley system. Percent error means that the difference between expected and actual results. Possible causes of error will be the friction of the pulley, unbalanced pulley, mass of the string, air resistance, motion sensor limitations, and all of these errors show that the real-life systems are not perfect and affect us. The people that contributed to this lab was Silemi Rivero by performing the calculations and editing the video, Danitza Canales by completing the PowerPoint and helping with taking pictures and videos, Diego Padilla by completing and helping with the experiment, Angela Aguirre helped complete the experiment, and Annika Wagner helped conduct the experiment as well.